Okay. Well, first of all, thank you very much to Paul for the invite. It's amazing who he'll get to invite to do a presentation after the second beer in the pub following the meetup event, which is my tip if you ever want to present here and get on the agenda. But
You say
quite the honour.
I'm bribed by beer. Is that
Couldn't possibly say. My name's Andy Hooper. Video Gig Limited is me, okay, just in case anyone's confused by that. Currently, what that means is I'm currently between jobs, just to be clear. I've been working in the digital video and media industry in various guises since 2007, and in IT for a good long time before that as well, despite my youthful appearance. I don't think I'm possibly not quite the person who's worked for the longest in digital media in the room, but we'll find that out later, perhaps in the pub. What I pitched effectively to Paul was a topic that I think is really interesting, and one of the things that I've been doing for the last few years is working for a couple of international hardware and software vendors who are doing some pretty interesting work in the whole space of evolving video production and delivery. And there's one particular project that I want to talk about at the end of the presentation, which I think is really an interesting benchmark potentially for where the industry could go. But to get to there, I'm going to tell you a little bit about some protocols. Okay, that's the boring bit probably in the middle. Probably a protocol you haven't heard of if you're on the technical side as well. And so actually my role today is to evangelize a little bit about a new protocol that I think could play a very important role. And equally, I'd like to hear from you if you think it shouldn't. That's an important part of the discussion that we can have in these events as well. But let me start off with a bit of history. So what might a cloud-native live TV production pipeline look like? Am I going to click the right button here? Is it off? No. Okay, we've got to go back to basics here. Oh, it's because I'm not on I haven't got the focus on the screen maybe. Hey, there we go. And I tend to put this whenever I'm talking to people. I mean, part of what I do in consulting is to talk to sort of C-level people in the industry about this sort of stuff, and they like to have nice, simple frameworks to understand things in. So I tend to see the way that we're evolving in the industry in three main buckets. You have the very traditional broadcast world that's existed for a long time. You have the effectively porting that to IP, and then you have the future, okay? And I think there are obviously grey areas between them, but those three, I think, tend to help framing things for most people who perhaps don't do this every day. The first one of them, traditional broadcast infrastructure, is not what you put in the cloud, just to be really clear, because it's BNC connectors and SDI and 1,448 gigabits per second, and what the hell? It's huge, megabytes per second. So you don't put that in the cloud. And indeed, the mindset of the broadcast industry when it was building these systems sort of finished at the play out and the contribution, and that was the end of it. So the broadcast industry has spent a long time working on standards and excellence in this domain, and a lot of that's not relevant for the future potentially as well. So this is kind of where I'm going to be going with the presentation today. You can't put much of that in the cloud because Amazon don't like it when you ask them to plug a BNC connector in somewhere. There's a lot of work been done over the last 10 years now on what the future of that environment is. And so a lot of you who are working on studio architectures in the IP domain may recognize this kind of picture. But the SMPTE 2110, ST 2110 set of standards effectively takes everything that was in that broadcast domain and recreates it with a standardized IP architecture underneath, okay? So you're kind of starting to use commodity platforms, commodity servers a lot more rather than specialized hardware. You're starting to use commodity networking hardware. You're starting to use IP. But the mindset that's gone into doing all of that is not that different from what went into building the traditional legacy broadcast infrastructure, I would argue. So the mindset is still very much the same. And you actually can't take much of this next generation IP stuff and put that in the cloud. Hey, welcome. Because it's too high bandwidth for one thing. It still respects a lot of the same engineering constraints that went into the excellence of broadcast from the first world that we put on the chart a minute ago. And I think when you start to look at the future, just to give one example, this is an an example from Sweden where I've been doing some work over the last few years. So SVT, the Swedish broadcaster that's kind of analogous to the public service broadcaster, kind of analogous to the BBC over there, they put a load of cameras in the wilderness in Sweden to watch the mooses migrating. And you might think that that's a bit of a niche thing, but it turns out it was hugely popular. Gamers on Twitch had alerts going off based on integrating with an API when a moose walked past the camera, and we're interrupting their gaming sessions to actually go across and show you the first moose across the river. Really stuff that you wouldn't have imagined being on TV, perhaps even only 5 years ago. Look at the view counts on that. It's pretty impressive, right? So when you're doing this kind of service, and you know all of this is going out on PCs, yes, but mobile primarily, right? I mean, this could easily have been TikTok on mobiles. So the question is, if you think about TV production, live TV production end to end, in a world where 95% of your consumers or viewers or users are actually watching on mobile devices at 3, 4, 5 megabits per second, and that's good enough, what does that imply for the production architecture up front? And a very different production architecture is the answer, ultimately. So, given that, given changing consumption patterns and given the fact that kids are watching TV in a very different way, we're all watching TV in a very different way, if you couple that with some emerging trends and some changes that are taking place around us, some interesting things start to emerge. So what are those other trends that are around us? Well, network quality and availability. So in particular, quality of mobile networks, quality and reliability of fixed connections, cost as well of those connections coming down continuously. So we have to be able to take advantage of IP, internet-based contribution, for example. Very high quality mobile device and camera platforms. I've heard some comments from broadcast camera engineers saying that they can no longer get the Sonys and the Canons of this world to say that they will be as good as some of the camera capabilities that are coming out in mobile phones these days for certain aspects of what needs to take place. Certainly those platforms are iterating and evolving faster, right? So taking the media from those devices implies, again, a very different workflow and a very different contribution pipeline. GPUs everywhere, so graphics processing capabilities that can be placed in various parts of your pipeline, okay, on commodity hardware with interesting things that can then take place. And of course, in linking back to the general cloud migration that's going on, the cost of compute and networking continually coming down, and a lot of competitive pricing pressure there. All of these things come together, and then you also start to think, well, maybe in certain parts of the industry, that adherence to those very, very highly specified engineering constraints that we've had over the last 40, 50 years can start to be loosened up a little bit now in the interests of exploring a new way to do things. Okay, so maybe we're starting to be able to imagine sacrificing some of those sacred cows. So, what does it look like? Well, if you start to sketch out the requirements for what it might look like, and one of the things I'm doing at the moment is starting to come up with a sort of requirements package that I can take to broadcasters and help them to articulate what this looks like when they're buying this sort of capability. So you need a very user-centric experience. You know, your responsibility as a content creator no longer finishes at the contribution. It goes all the way to the human who's actually consuming that content at the end. And you have to think about this whole service that's being delivered now, and not just the fact that you are getting a signal and handing it off to somebody else at a certain point. There's all sorts of different engagement concepts. We saw the example of the Great Moose migration, but there's thousands of them that we're all aware of. You want a CTO-friendly proposition increasingly as well. And that might mean, very interestingly, that your quality, latency trade-offs and the cost of your production pipeline can differ from program to program according to the value that it's delivering the business. And again, that's a real mind shift difference compared to what we've done in the past, where we've stood up these systems and it's one size fits all for all the content that goes through. And you know, I think there's a notion that more content in good enough quality is probably better in a fragmented consumption world than little content in very high quality, okay? Because you want to be attacking all of these different niche markets. The sources that are coming in now and being able to be used to contribute to live TV are very different. And if we're trying to take sources from cameras like this, or GoPros, or drones, and put them into a traditional TV production pipeline, again, we're spending time translating standards and codecs and so on, and it's very inefficient. Why not just be able to take that content natively out of that device and splice it straight into a live program feed? And there are some big IT goals in all of this as well. So we heard a lot about the IT and the DevOps side of this, but the IT world is moving very fast towards producing very efficient and increasingly very agile ways of working in all of these domains, so that you can change and iterate what you're doing on increasingly short timescales. And this slide is basically talking about all of that. And one of the goals of the project that I'm going to talk about is ultimately to be able to have one remote person being able to be the producer of each piece of live content that's going out, and do that from pretty much anywhere. Okay, so that's a very big mind shift difference again. Conscious of my 20 minutes, I'm keeping moving, Paul, don't worry. So we're missing a little bit of the edges here, but this is the broad scheme of it. So if we start to sketch out what an architecture for live TV production in the cloud might look like, and we've got a cloud on the chart, so that's okay. I mentioned all the different variety of sources, and some of those, of course, can be traditional broadcast sources, okay? So we have to be able to include those in the mix as well. We've got a whole raft of different standards that can be used to capture and encode video, to then encapsulate and transport video. We've got standards, if we're assuming that the internet is the contribution network here, rather than any kind of fixed connection, we now have standards such as SRT and RIST, which you may be familiar with, which add reliability onto UDP to allow us to actually recover lost fragments of video, okay, when we're contributing into the cloud. And we start to be able to sketch out an architecture of which this is the most simplified version that I've come up with, which looks like a bit like this, but you effectively mirror the functions that you've got in a traditional live TV studio environment, and you make software components running in the cloud, and crucially you put APIs on top of everything. Application programming interfaces that then allow you to orchestrate those resources, instantiate them when you need them for particular programs and pieces of content, and tear them down again when you're no longer needing them and using them, because you don't want to be paying for them when there's no TV going out, right? Your TV production team is not in the cloud, they're somewhere else. They're at home, or they're in a studio, or they're in a production control room. So there is a backwards and forwards that's needed here. And of course, ultimately, you have to distribute all this as well. So sketching that out is the easy part, but then you start to get to the next level and find out what the problems are. So first and foremost, that 40 years of broadcast engineering gave us some very standardized ways of synchronizing inputs in order to be able to do switching between inputs and create clean outputs, right? Gen locking of cameras and so on, right? And sources. So if you're actually taking sources from lots of different types of device in different formats, one of the first problems you're going to come up with is timing and synchronization. Okay, how do you know, if you're the producer sitting here, that the clock that's coming in from these sources is aligned, and so that when you actually make a production switchover decision, that what is affected in here actually is what really you wanted to do. Very non-trivial as a problem space, okay? And it is not solved by SRT and RIST. That just gets the content into the cloud, okay? Multiplexing of stuff as well. So if you've got a number of cameras and commentators and so on at a football stadium, for example, then sending all of those sources individually via RIST channels is probably not going to be the most effective way to do it. You're going to want to multiplex that and make better use of the available bandwidth that's taking the content out of the stadium into the cloud, okay? So multiplexing is another big problem. Again, these protocols do not address that at all. If I was the CTO of a broadcaster, I'd probably want some path resiliency. I'd want to be able to send it via 2 different routes, so that if one route went down, the football game was still reaching the TV screens at the end of the day, right? You're starting to be able to do some bonding within RIST and SRT of paths, but again, you need a whole load of extra work on top if you want to fundamentally send the same video via different routes and then recombine it into one master stream once it reaches the cloud, okay? Again, pretty tough. Somewhere you need a directory, you need some kind of metadata, Okay? How many cameras are out there? Where are they? Am I including them in this production or not? So there needs to be some kind of registry, some kind of capability that you build which ultimately knows about all of these sources and makes them available to you as a production manager in order to be able to get them into the feed. You may not have much bandwidth down here. Okay, so if you're sending tens of megabits per camera up into the cloud over here, you're not going to get all of that down to here. Okay, but if you've only got a 5 megabit per second home internet connection down here, and that's where you're trying to do your production management from. Okay, so the bandwidth there is most likely limited. Resource abstraction, so all of this needs to be actually ultimately hidden behind APIs, but then made available in some kind of, again, it's linked to the directory, but this is really about going to the lower level now and actually making all of this available with some kind of common ontology that makes it addressable. And then going forwards, well, pick a workflow or a piece of a task that happens in a typical live production. Every single thing that we currently do with audio, voiceover, commentating, replay, color management, hue, saturation, all these things, we have to find solutions for all of those things in this domain as well. So there's a lot of work to do in here, all right? So, given all of that, I come on to sort of part two. Hopefully I'm not taking too long, Paul. How am I going for time? Got like 10 minutes left? Okay. So, the team that I was working with up in Sweden actually came up with a pretty, I think, innovative approach to addressing this problem space. And what they kind of fundamentally realized was that the problem is so big that it does warrant some pretty low-level work, to the degree that they cooked up a new protocol to help address that problem space. And I wanted to talk about this and introduce it to you today from an education and awareness point of view more than anything else, at least to put it on the list of things you might spend time investigating a little bit more. I'll tell you a little bit about it, and there's all sorts of opportunities to learn more. But fundamentally, Elastic Frame Protocol is quite an innovation that I believe has an important role to play going forwards in this whole domain in solving these problems that we have. And really, it was created in response to this question. Okay, so theoretically, if we forgot, I haven't mentioned MPEG-2 transport streams yet, but I'll come back to that in a moment. If we forgot, though, that they existed, and we had to design a modern media multiplexing and framing protocol to support live TV production for internet and cloud, what would it look like? Okay. And so the set of design criteria that have gone into EFP are fundamentally about trying to address that problem statement. Okay, so it's relatively fundamental in terms of addressing this whole space. Hopefully most people in the room have heard of MPEG-2 TS. It's somewhat pervasive in our industry. If I give it the 10-second version, it is the media encapsulation and multiplexing standard that is pretty much everywhere, supported by pretty much every encoder that you might find out there, every set-top box that's out there that ever existed in an IPTV system, for example. And it's the encapsulation protocol for passing programs of elementary streams through normally a constant bitrate connection, okay? And it's used very pervasively. And where you see SRT and RIST being discussed as the means to get content into the cloud, it's normally an MPEG-2 transport stream that is the wrapper for the media that's being passed across that resilient link, okay? But MPEG-2 DS has a few problems when it comes to modern media workloads. I mean, a lot of people will kind of say that I'm mad suggesting that you might do away with it. It's that pervasive and that fundamental to a lot of the work that we do. But it does have some issues. It was designed a long time ago. I can't even tell you how long ago, but it was designed at the most low level for ATM networks. So the most atomic thing that you can create in an MPEG-2 transport stream is a 188-byte fragment with a 4-byte header. Everything you do has to fit within one of those 188-byte frames. And it was designed for ATM cell payload sizes, okay? We don't have ATM networks anymore, we have IP networks. And it's not very well suited and not very efficient for IP networks to run MPEG-2 TS 188-byte frames across them. Okay, and I've got some examples of that. If you're running at a constant bit rate, which is the normal way, you still have to fill up those frames. So variable bitrate video going within an MPEG-2 transport stream ends up having lots of null stuff put in there. So again, you're using your scarce internet bandwidth for empty packets, fundamentally, if that's what you're doing. There's a number of other functional issues that you can look at. So out-of-order delivery is not something it supports. It tends to have just the throw it all across as fast as possible kind of mentality and repeat. And there isn't really any sense of loss. It only has 4-bit control codes, which means that you're going to find it hard to reconstruct data on the receiver side in the case of loss. There are already some alternatives that you can start to look at, but none of them are what you might call perfect for internet applications. So a lot of them are bound to a particular underlying transport, and wherever we go and work, we find that we have to use different transports. Some of them suffer from head-of-line blocking, but you might want to not have head-of-line blocking. You might be able to send the media as soon as it's available on the network queues. Most add unnecessary headers for the purpose at hand of getting the media into the cloud. Okay, and I'm going to come on to what that is. And this is kind of an important one, but when you look at the actual licenses that a lot of these solutions are actually released under, they may not be desirable to have in your solution, depending on your particular use case. Okay, so a lot of open source licenses are not particularly friendly for technology vendors to incorporate in their own software, for example. So, a lot of what I'm going to talk about now is about EFP for the next couple of slides. And first point, linking back to the previous chart, is that it's released under a very friendly open source license. It's called the MIT license. If you're familiar with that, it basically is one of the most permissive open source licenses that you can use. The only thing you have to do if you take this EFP software and put it into your own product and then go off and sell it, the only thing you have to do is put a relatively short copyright notice into the build, and away you go. You don't have to re-release the source code. You don't have to restrict what you do with it commercially. It's just a copyright recognition. That's all you have to put in there. Okay. So you can do pretty much whatever you want with EFP. You can take it off into a new protocol if you want. It supports fundamentally flexible framing. So the whole logic of the thing is to look at the media that you've got and the network that you're running on and allow you to adjust the size of the frames. You remember I talked about MPEG-2 being restricted to always being 188 bytes? EFP is designed from the ground up to be flexible in what you do. Okay? So much more efficient use of the network resources according to the media type that you're using. Multiplexing of multiple media streams is fundamentally what it's all about. And already there are some plugins, there's the plugin architecture built into this thing, to enable you to bond interfaces together. It can already support things like 1+N link protection, dynamic load balancing. You can either split media across multiple connections, or you can duplicate it and it will reconstruct it into one master source when you get it into the cloud for the application, depending on what you need to do. There's also a signaling plugin, and that enables you to do some pretty interesting things, like, for example, from the cloud side, telling the sending infrastructure not to send certain audio streams, for example, or not to send certain video streams because you're not interested in them in your production. So whereas today, if you look at a lot of the applications or projects that are sending media into the cloud, that's a relatively static setup once it's in existence. This allows you to actually send a remote API call to the sending box and actually throw away some of them at the source side, thereby maximizing your utilization of that network connection to the value of the content you want to produce. It's all open source. The links are on here. So if you want, ping me, or I'm sure you can get it from the video afterwards, what those links are to go look at the actual GitHub project for this. A few of the benefits, and I'm taking these benefits from a paper. So there's an IEEE paper that's been submitted by the team that invented this. I think it should now be available on the IEEE website. If it's not there, it will be very, very soon. And what they've done is effectively done some comparative, detailed technical analysis that you can go review if you want to get into that level of information. And you can look at what some of the test results are. To cover those to some degree, here's a quick overhead comparison. So, ran some tests comparing EFP and MPEG-2 TS. The MTU, i.e. the minimum transmission unit for the link, was set up to be optimized for the networking use. One elementary video stream running at 50 frames per second with a range of bit rates. One audio stream, AACLC at 96K, and even ignored the fact that MPEG-2 TS would have to stuff null packets in, okay, so it would be even worse but you can see the kind of, at low bit rates, difference in overhead, so the payload overhead of all the headers that you need. By the time you've added all the stacks of protocols up to get to MPEG-2TS, very significant at low bit rates. And you can see that they're both trending towards a sort of asymptotic level here, and those are what those levels are. So EFP running at 1450 bytes compared to MPEG-2TS at 188, and it's effectively a 4 times improvement, okay, at higher bit rates even, all right, which is very considerable when you're using scarce resources like internet connections to do your contribution, I would argue. Okay, it means that you're going to be much more reliable in your, think the RIST protocol that's running across the EFP is going to actually be doing a much better job of protecting your quality if actually your overhead is that much lower. Okay. Rushing through a little bit on the topic of some of the other benefits. Timing. MPEG-2TS was designed in a world where you had to send the clock with the stream. Okay, so there's a thing called a PCR, which is a reference clock, rolls over every 26.5 hours. The way that they've designed EFP means that it uses TAI, which is part of the global UCT time standard. It's a monotonically increasing clock every second. There's no leap seconds or anything like that. So if you take a timestamp with TAI, it's always valid, basically. Okay, you never have to correct for any leap seconds or anything like that. It works across the internet, and all the nodes can be synced together using standard internet type protocols. Again, very important for cloud type applications. The interpretation of those timestamps is then left to the application. So this is an area where perhaps things need to be evolved a little bit, and there's certainly a lot more work to do in all of this, by the way, just to point out. But not as good for interoperability, but you can choose to do a lot more with it as a result. So once you have your media with these timestamps, your application can do a lot more than it would be able to with MPEG-2TS timestamps. And there are then some downstream distribution benefits as well. So it aligns quite nicely with ISO BMFF containers, if you know what they are, which is part of MPEG-Dash, for example. So you don't have to do less translation at various points in your workflow. Better error detection and recovery because it includes 2 layers of 16-bit error correction packets compared to the 4 bits in MPEG-2TS. Okay, so you can actually do more error correction without necessarily having to do retransmission. Okay, again, it's going to be application dependent. Better sorting of duplicates, better multipath delivery. The descriptive metadata in an MPEG-2 transport stream, if you're aware of that, is sent continuously in the stream. And according to the system that's using it, like in DVB, it has to be sent every half a second. So every half a second, you're sending redundant data again and again and again. Why? Because if you plug in a set-top box to or any kind of receiver into an MPEG-2 transport stream, they want it to be able to gather its own program data from the stream as quickly as possible as soon as you plug that stream into that box. Okay? But with full duplex networks now, we can do a lot more interesting things than that. Right? We can start to actually do the signaling out of band, so it supports web sockets out of band, or you can actually send it within the stream itself. And I mentioned already the whole thing about signaling the sender to only send the things you're interested in. Okay? So this is more than just a protocol that's on paper at the moment. It's also now being built into a real project. Okay? And so this is the part where I was working with Agile content for the last year and a half and became very aware of this project. It's very interesting. And I truly believe that EFP itself is something that can be very beneficial to the industry. So that's my advocacy piece here today. But to give you a quick flavour of what's going on, the CTO of SVT up in Sweden is a kind of very innovative guy. He's pushing them forwards to investigate lots of different ways of doing things. And they have used now EFP as the basis for a new live production pipeline. Okay. So to give you a couple of snapshots of what it looks like, they've built a capture application, okay, which is the remote application that sits out on the site where the source of the video is coming from. So they've built that on GPUs, okay. The sources are coming in and being homogenized to a standard capture bit rate, okay. They're using RIST, I think, primarily, but SRT is also supported, running across EFP, all right, because EFP is the multiplexing and framing, but then you still need that resiliency on the link. And dynamic encoding with remote API control. So if you decide that you want to lower the bit rate of something because it's a less valuable feed, you can do that and it's all dynamically controlled in real time. It also creates two different versions of the stream, and this is the crucial thing that I think now we need for live production in the cloud, right? So it creates a high quality version over here, which is what the actual program out will be created from. All right, so they're tending to do that at around 50 megabits per second, I think, at the moment, because they're using broadcast cameras in the first phase of the project. All right, so they've got SDI going in here, by the way, into an SDI capture card, and I think they're doing 6 cameras per box, and it's a NVIDIA GPU on a €2,000 commodity server. If that helps you to frame the kind of scale of what we're talking about. They're also sending a low bit rate, low latency stream, and that's what's used for the actual production control. Okay? So I'll give you an alternative view of this, and then building the applications around it in a bit more detail. So you've got this one new box, okay, taking 6 camera feeds, producing 2 encoded versions, time-stamped with TAI timestamps so that you know that both versions are completely aligned later on in the process. You've got the ability to do exactly the same with additional offsite sources. They've prototyped it coming out of an app on an iPhone, straight into the cloud over a mobile network. You bring it into your low latency production pipeline, which is running at 1 megabit per second and about half a second of latency. Okay? Your 3 to 5 megabit per second internet connection, you then have a multi-viewer. Okay, and next step is to use WebRTC to present that into the web browser. Right now they're using some other method, I can't remember what it is. But fundamentally a control point here, very similar to what you would see from a traditional TV live production control console standpoint, to actually send the control commands back to the low latency version. And then the low latency version proxies those through to the production version, which is running at 50 to 100, it says here, megabits per second. I think they're more like 50 at the moment. And that's running at 3-second latency. Okay, so you can start to tune the latencies and the quality depending on your applications, because all of this is API controlled and dynamically controlled. And obviously the controllers, the producers here, are running ahead by 2.5 seconds of what's going out on live. So if one of the cameras suffers an issue, they've got 2.5 seconds to switch to another input. That then hits the production pipeline and then the program out. Okay, so it's a really interesting application of EFP, which is enabling all of that within this software suite. They've got a lot left to do, though, and I think we all have a lot left to do. If we're going down this path, what I've just showed you, I think is a huge step forwards, but there's a lot left to worry about. In particular, audio is difficult to bring into this environment, okay? If any of you have done some audio engineering and tried to do it in the cloud, you're going to know a little bit more about that than me. But they're also then looking at trialing with 5G. You can start to imagine collaborating quite nicely on 5G networks with the telco providers, for example, because wouldn't it be nice if, you know, rather than having to use the stadium Wi-Fi, which is typically pretty bad, you're getting a 5G network slice with a registered application in partnership with a telco provider, so that those fans who are walking around with their mobile phones at the game are getting guaranteed bandwidth up to the mobile network in order to contribute to the live production. For example, they're going to start building in some WebRTC to deliver out the production switching environment. Various improvements in the link capacity optimization, redundancy, and so on. As soon as you've got all of this in the cloud with API level control, you start to be able to use generic cloud capabilities such as AI to do some of the things that today potentially are manual processes like color adjustments and so on. Could be an interesting application of that. So if the machine learning models you can build on the AI capabilities of platforms like AWS and Azure are very well suited to looking at a piece of content and trying to work out if it fits in one of multiple categories and then automatically applying various color corrections to it, something that today is quite a manual process, right? Graphics, another interesting one. So they're incorporating Unreal Engine, I think, at some point to try and do some of the graphics overlay on this. Subtitling, all these things are obviously part of the standard broadcast workflow, need to be improved, enhanced, and added on. Replay, not the most straightforward in this environment, okay? So doing replays is another work item. And all of this is something that I think would be very hard for just one project to get right on its own. So hence my pitch to Paul to come and tell you about it. I think it warrants a bit more collaboration and a bit more thinking. And we need to evangelise a bit more, because there's a lot of things that I think we can come up with almost as a standardised architecture here as an industry going forwards, which can lower the time to market for this kind of capability going forwards as well. I think, in closing, I would like to say pretty much what I just said. So EFP as a protocol, I think, does warrant investigation. I urge you to take a look at it. The current activity levels are not huge. You know, it's kind of limited to this project that they're doing with SVT. Has been picked up by Fubo TV, so it's not just isolated in Sweden. There are some other companies that have come across it and found it interesting. Okay, interoperability is not there, right? It's not, you know, you can't pick a piece of equipment up and it's not going to support EFP, right? So unlike a lot of what you already do today, this is going to be a difficult thing to build in. But if you are someone who runs a live production TV service and is spending money building your own capability and investigating this, it could be very, very interesting for you to investigate, I think. And I think the SVT project is definitely worth tracking. They're going to be, I think, presenting it at IBC in the main conference facility. They've now got an election in Sweden. It was originally due to go live for the first local news production sort of around now. And I think they've now got an election, which means they've got a freeze on all of their IT. So they're not changing anything over the summer. And they're looking to launch it now in the autumn, I think, post-IBC. But I'm sure that they will present that themselves at the show. So I covered this, you know, if we can sacrifice some sacred cows and if we can start to look at this a bit differently, there's a huge amount of value to be gained here. And, you know, here it is on a timeline. You know, all the spend, all the money we spend on technology, if you go back to, you know, bygone eras, pre-2015, it was all that first BNCs and connectors type stuff going on, right? It was all the traditional broadcast architecture. And then all of a sudden, all the money's being spent on broadcast over IP. And we sort of find ourselves here now with little projects like the SVT project that I talked about. But it's my sincere belief that at some point over the next few years, we'll hit an inflection point. And once the cost benefits and the flexibility benefits that are inherent in this kind of architecture become more widely understood, I think we'll find that the world will start to look more like this. So I'm not a prophet, I'm not going to tell you when, but I think that inflection point does exist. That was probably much longer than 20 minutes, but hopefully it was useful. Thank you.